So we're going to be taking a look at the final exam for fall 2017, and we're going to look at question 6. This is a work-related problem. Okay. On this particular question, on this particular problem, we're taking a look at the work required to pump some kind of liquid out of a tank. The tank is in the shape of a right circular cone, and the tank is inverted. So we're given the shape, the right circular cone, and it's inverted, which means that the vertex is down, kind of like an ice cream cone. And the cone has a height of 12 feet. It has a radius of 4 feet. Okay. The tank contains a liquid with a density, a weight density, we're told 63 pounds per cubic foot. Okay, so because it's in pounds, I don't have to worry about taking into account gravity, because pounds already has gravity included in it. And it's filled to a depth of 8 feet. Okay. We're going to set up a down evaluate, go for the work, and foot-pounds are required to pump all the liquid to a height of 1 foot over the top of the tank. So we're going to go plus 1 foot over the top of that tank. Okay. Basically, when we do this, okay, so we're going to set this up. Let's see how I'm going to do this. Okay, so I need to think about the area of the base. This is going to be pi r squared. Okay, but the problem is that my radius, okay, my radius is only like 4 at the very tippy top. My radius down here is going to be smaller, it's going to be smaller, it's going to be smaller. So I need to come up with a way to relate the size of the radius to the height that we're actually at. So when I think about setting that up, I'm going to think about similar triangles. So in this particular case, I've got, I've got a triangle where I've got a radius like, so there's 4, here's 8. And then the other triangle that I want to think about is, here's my radius, and then here's the height that we've actually done. So my similar triangles are going to set up like this. Oops. So to actually relate them together, I'm going to say my radius has a height of 4, when my height is equal to, 8. Okay, this is variable, actual, variable, actual. Okay, so I'm going to solve for radius, or h over 8, which is equal to h over 2. Okay. Did I write that down right? The base radius. Okay, good. All right, so here's h over 2. So let's go ahead and plug this in. So the area of our base, pi r squared, is going to look like pi times h over 2 squared. Okay. So now what I need to do is, I have the same r over 3 for this. Oh, it has a height of 12. Yeah, that's right. It has a height of 12. My bad. Okay, that's good. Okay. And this is 12. And this makes it h over 3. Sorry about that. And that's a 3. Good. All right, so that we're going to use. Now, to calculate out the work required, okay, the volume of liquid that we're going is 8, 0 to 8, right, because that's how we're doing this here. Now, we've got pi r squared times our weight density times the distance. So the distance that we need to go is 12 plus 1 minus the distance where we're actually at. So if I've gone, the liquid here only has to travel this distance, whereas the liquid here has to travel the whole distance. This is going to be 12 plus 1, 13, right, minus the height that we're actually going to use in terms of h. And then dh is going to be our little sliver, okay? That's the little sliver of thickness of our circle. Okay? So let's go ahead and plug this in. So this goes 0 to 8 pi r squared, h over 3 squared, times our weight density, 63, times 13 minus h, dh. I think they did things in terms of y, but you can leave it like that too. And now we can actually, multiply these things through. So this becomes 0 to 8 pi. This is 1 over 3 squared. This is all over 9. This is h squared times 63. 13 minus h, dh, right, 9 goes into 63. I can clean this up. 0 to 8, 7 pi, 13 minus h squared dh. If you want to be able to take a look at that. and compare it to the solution set. That's where we get it. They did it in terms of y. It doesn't matter what variable you're using. And then there you have it. We don't actually have to evaluate this integral, but if you wanted to evaluate this integral in your calculator, you would obviously use this as your variable. Okay, and then you could plug it through and actually get a value. And we're not asking you to do that in this particular case.